Hey, welcome to Advanced Mechanics. We're going to be looking at our new topic, which is going to be the Lagrangian mechanics. So let's just jump into it. Lagrangian mechanics is a way to describe dynamic systems. So one way to describe systems that are accelerating, objects that are accelerating, is using Newtonian mechanics. So that would be the Newtonian formalization, which is just F equals ma. There's another way to describe objects that are accelerating or dynamic objects, which is using the Lagrangian formalization. And that's the one that we will be looking at going forward. Once we've done the understanding of this and then also several example problems, I will then go on to a third formalization of describing dynamic systems, which is called Hamiltonian formalization, which we'll look at later, and that'll be Hamiltonian mechanics. So Lagrangian mechanics is where we're going to start. There are other videos that go into deeper understandings of where the derivation comes from. I'm just going to give a simple explanation to it, so that way we can use it to solve some questions. And it is easy to solve questions in certain situations using this method versus Newtonian method, especially when systems get really complicated. Newtonian mechanics is a nightmare to work with. So instead we use Lagrangian mechanics instead, or Hamiltonian. So Lagrangian mechanics, the Lagrange of a system, L, a Lagrangian, that's what they say, is equal to the kinetic energy minus the potential energy. So this may seem weird to write at these letters, but these are what they're used in the textbook. It's either T minus V or T minus U, where T is the kinetic energy of the entire system. So that's kinetic energy. And V is the potential energy. So if you like, we could write it like this: Ke minus V minus PE. So either way is fine. That's the first thing. This is the Lagrangian of the system. The equations of motion can be determined. The equations of motion for a dynamic system can be determined using this equation right here. Then once we have the Lagrangian, we would use this equation right here, d dt of the partial derivative of the Lagrangian with respect to some generalized coordinate q dot minus the Lagrangian of q is equal to 0. So this is the generalized position, and this is the generalized velocity of a system. It could be angular position and angular velocity, or it could be just linear velocity and linear acceleration. So the q and the q dot represent the position velocity of the generalized coordinate system. So that could be for all the velocities together. We use this letter, or sometimes we don't use it like this and this. We could use it in, say, for example, some systems will just use x and x dot, which is the velocity of the systems. And that's kind of typically the way I'll write it, but I just want you to see this because this is the way a lot of textbooks will write it down. For our situations, we're just going to write it in terms of x and theta, where x could be the combination of x, y, and z. All right. So the first example we can use to show this, oh, and before I actually show the first example, I just want to tell you what the meanings are, and then later you'll have a better understanding of why this is true. So this term right here inside the parentheses is actually just the generalized momentum. And this right here is a force. So what we have is the change in momentum over time, which is a force, minus the force right here, is equal to 0. And really, the Lagrangian formalization is just another way of writing F equals ma, except you're not really dealing with forces, you're going to be dealing with energies. And why is dealing with energies so nice? It's because you don't have to worry about the direction a lot of times. So we have force is equal to force. That's where that idea is coming from. The actual derivation is not something I'm going to be going over in these few lessons. Maybe at the end I'll talk about it. Okay, so the first example, let's see, example 1. is going to be, we have a ball of little m, and it's going to fall a distance y and hit the ground right here. So what do we know? This is an easy free fall situation here. This ball right here is going to have kinetic energy, Ke, which is equal to 1/2 mv squared. And it's going to have potential energy given by the equation Pe equals mgy. And we need to set our potential energy somewhere. So I will make the potential energy equaling 0 right here. This is going to be our minimum potential energy. All right, so anything above that is going to be a positive potential energy. So what we need to do is we need to write these two terms in their generalized coordinates. So the generalized coordinate of this would be written as 1/2 mx dot squared. And over here, the generalized coordinate in the y direction, which isn't a velocity, it's a position, we'll write down as mgx. Okay, and x just means any direction. It doesn't have to be like the x direction per se. It's a generalized position and a generalized velocity. So once we have that, we can put it into our Lagrangian. The Lagrangian is simply the kinetic energy minus the potential energy, which is going to be 1/2 mx dot squared minus mgx, and that's it. That's our Lagrangian. So now what we need to do is plug this Lagrangian into the partial derivative here and here. Let's do this term first. The partial of the Lagrangian with respect to the generalized position. That's the generalized position. In this case, x is our generalized position. So we look at our Lagrangian. This is x dot, so we don't, this is a constant when you're taking it with respect to x. So this term goes to 0. And over here, we end up with negative mg, and then the derivative of x is just 1. So here we end up with negative mg, and that's it. All right, let's do the other part now, this side right here. So the first thing we need to do is take the partial of the Lagrangian with respect to the generalized velocity. So let's do that. Over here, this term goes to 0 because it's not an x dot. Over here, we have an x dot. So when we take the derivative of x dot squared, we end up with 2x dot. So the 2x, the 2 at least, and the 1/2 will cancel each other out. And we're going to end up with mx dot. So are we done? No, we have to take the time derivative of this. The time derivative, dt of mx dot, is going to equal, well, if x dot represents the velocity, and if you take the time derivative of velocity, so if you take the time of velocity, you get acceleration, which is x double dot. So when we take the derivative of this, this just becomes x double dot. So we end up with mx double dot there. And now we have basically everything that we need to do for our Lagrangian. We're going to have this, which is this term right here. So I'll write that as mx double dot minus, because there's a minus sign, this term, which is negative mg, and that's going to equal 0. Okay, great. So what do we do from there? Well, this term right here, you could bring to the other side, and we end up with mx double dot is equal to negative mg. The m's cancel out, and what we're left with is x double dot is equal to negative g, where g is 9.8 meters per second. So we have g equaling 9.8 meters per second squared. So the acceleration, since we're calling up to be positive, the potential energy was 0 here. This is the positive direction here. The acceleration is going to be negative 9.8 meters per second squared. Well, that's great. So what do we do after this right here? We could figure out the position and the speed of this falling object here. This is pretty straightforward. I mean, we don't have to do all of this. We kind of know this from Newtonian mechanics, but I want to show you the idea behind it, the actual way to do it. So that way, when we get into more complicated situations, you'll understand why I'm doing what it is I'm doing. And is there anything else that I want to say? How does why does the Lagrangian work? If we go back to our example right here, we have dl over dx dot, that's what this is equal to. Well, this is just mass times velocity. This term right here, which is this, is equal to mass times velocity. Mass times velocity is just the momentum. And if you take the derivative of momentum with respect to time, you get a force. How about over here on this side? We ended up with dl over dx. Well, when we did that, we ended up with m times g, which is the weight. So this is a force. And really, if I bring this term to the other side, what we're really saying is F, or I guess we could say MA is equal to all the different types of forces. This is going to be all the variation of forces. This is going to be the acceleration, the net acceleration times the mass on this side right here. So this equation right here is exactly the same as saying F equals MA. And there are times where you can just write it like this. Actually, it's probably a good way to understand both directions, but I'll call it x dot here, is you just bring this to the other side right here, like that. And this is MA equals all the different types of forces. In this case, it was MA, because x double dot represents acceleration, is equal to the weight. That's just one, but you can have several different forces acting on the object. This is a very simple equation here. So that's what it is. It's equivalent to F equals ma, but we are solving for the equations of motion of the object from its energy. So we're looking at it from the energy's point of view instead of the forces. Okay. What could you do once you have this value right here? Well, we know that acceleration, how do I want to say this? The change in velocity over the change in time is equal to acceleration. In this case, the acceleration is negative g. Oops, sorry about that. So that's what this is equal to. And then we can figure out what the position are and the velocity are. So if we wanted to solve for velocity, I would bring the dt to the other side. We end up with dv equals negative g dt. And then you can just integrate both sides. Which way do we want to do this? If we do it without the limits of integration on both sides, we're going to have to add a plus c. So I don't want to add the plus c. I'm just going to put the limits there. We'll say the starting speed is v naught, and the final speed is going to be v as a function of t. Over here, we're going to have 0 at time equals v naught, or time equals 0 at v naught, and then time is equal to t at v as a function of t there. So we solve for this, we just end up with v as a function of t minus v naught is equal to, over here, we'll get negative g times t. And then what could we do? Well, we have one equation already. This equation right here, using Newtonian mechanics, is just v final is equal to v initial minus gt. Or you could write plus at, whichever way, it's fine with me. But we got that from first getting our acceleration equation and then working backwards from it. Now we have the velocity of the object. We can also determine the acceleration of the, not the acceleration, the position of the object by saying that v as a function of t is equal to v naught minus gt. And this, let's see here, what do we want to say? This is equal to dx over dt. So we bring the dt to the other side and we get dx is equal to the v naught minus gt parentheses dt. And just like we did before, we can evaluate our integral. So this is going to go from 0 oops, not 0, x naught to x as a function of t. And over here, we're going to go from time equals 0 to time equals t. Here we end up with x as a function of t minus the initial position. And over here, we're going to end up with v naught t minus 1/2 gt squared. And this is another equation that you should be familiar with. This is just delta x is equal to v naught t, this should be a minus, plus at squared. So we got this equation back, and we got this equation back. Where is it? That we use in Newtonian mechanics that you learn in high school. And we did all of that because we first understood that acceleration was a constant. All right. So that's it. Is there anything else I wanted to say? Maybe I could say this really quickly. There are certain examples that we can look at that are pretty interesting for practice. One of them we just did was the free-falling object. So you have an object with mass m. It's got a velocity v is equal to x dot, and it's going to fall some position. So we could call that x right there. This is the generalized coordinate. And it doesn't matter. You could call PE up here or PE down here, as long as you're consistent with the signs. And so we could get our Lagrangian here, which is just going to be L equals T minus V. And this was the 1/2 mx dot squared, mx dot squared. We're going to subtract from it mgx. Okay, so that was the Lagrangian there. And then what could we do with that? We could figure out what the forces involved in here are. So the forces is just going to be dl over dx, and that's going to be 0 minus mg, and that is the force due to gravity. All right. How about another one? How about if we had a spring? We'll take a look at the spring one again in the next video, but let's quickly just write it down so we have an idea. So here you have a spring with a block M attached to it, and we could call this the equilibrium position, x equals 0, and the object has some velocity, v equals x dot here, and then I think that's it. We could write down the Lagrangian, which is L equals T minus V. In this case, it's going to be 1/2 mx dot squared minus the potential energy of a spring, which is 1/2 kx squared. And if we want the force, dl dx right here, this term is 0. This term is going to become negative kx. And guess what that is? That is Hooke's law for a spring. This was the gravitational weight of the object. And it doesn't have to be just like this kind of system. We can also look at Coulomb's law. So with Coulomb's law, you have a big charge, which we call big Q, and we have a little charge here, we'll call it also positive, little q. And so how would we write down the Lagrangian here? Well, what's the potential energy of these two right here? The potential energy is simply just the work done, which is Q times delta V. And that's going to be the same as saying Q, K, big Q, little q, over X. Normally we say R, but X is the generalized coordinate here. So if we write down our Lagrangian, the Lagrangian is going to be 1/2 the mass of whichever object we're interested in. So it'll be m x dot squared. So what we'll say is this is so heavy, this isn't moving. It's going to be this thing that's going to be moving, minus the potential energy, which is k q little q over x. So what's the force going to equal? dl dx. This term is gone. This term right here, you bring the x to the top, which becomes negative, which becomes x to the negative 1. And then when you take the derivative of that, the negative 1 comes to the front, cancels out the negative here, and the negative 1 becomes a negative 2. So we end up with k big Q little q over x squared, and that is the electrostatic force. So this is the gravitational force, this is the force due to a spring, and this is the electrostatic force. And that's using Lagrangian systems here. So that's it. Hopefully you have a better understanding of what this Lagrangian is. It's the same thing as F equals ma, but we're using energies instead. After this, we are now going to look at a bunch of questions where I set up the Lagrangian and I'll write down what the acceleration will be. Maybe for some of them, I'll actually work it out like I did in the last example, what the position and the velocity would be. But for the most part, I'm just going to set up the acceleration part of it. And it can get complicated, especially when you're dealing with partial derivatives of very long equations and then you have to solve it. Doing it by hand is very long and tedious. If you've got a computer, it's usually faster to do it that way. But there it is. Is there any other thing I want to say? There is one more thing I want to say about the Lagrangian, and it is that it is not only used in advanced mechanics like we're doing right here, and not only used for complicated dynamic systems, it's also used in quantum mechanics. So we write down the Lagrangian, more specifically this thing called the least action principle, and that has to do with having a Lagrangian there. So not only will you see it in this class, you will see it later in quantum mechanics and also in quantum field theory. So it's a very important formalization that you want to get good at understanding. So that's it for this lesson. I will see you in the next one. Take care. Adios.